Okay, so some interesting things have been going on Zulip. Especially, there was a proof by RT that starting to grasp the connection with this idea that eta rules correspond to some kind of uniqueness. And I should clarify that here uniqueness, I don't mean that there is only one eta rule. It's like the eta rules of each type somehow give an aspect of uniqueness to this type. And what RT proved here was that, okay, usually you see something like that. W is equal to W prime, as if it's a definition. It means that they agree on the projections. And actually, the surprising maybe thing is that the interesting thing is that this is not a definition anymore. This becomes a theorem. And RT proved the interesting direction, which is, which one is the interesting one? It's this one. The other one is quite trivial because, you have equality here, which means that you can substitute equals for equals anywhere. So this becomes very trivial. The real interesting part where you actually use the eta rules is the other direction. And this we did that on Zulip, and the idea is that we'll do similar things on other types as well. So, on the other front, we are studying induction and recursion, and we have seen that induction and recursion are not like things of the natural numbers only, but we have met like induction at least for the Booleans as well, because we managed to say what induction like really means deep in our heart. It's like all constructors preserve something, and if I have it, it means that every element of this type has this property. I haven't talked about lists, and I don't want to actually get much into this because I will bore some of you to death, but some people have never seen what a list and don't know what the concept, so at least roughly I will describe what we expect of lists. And when I say list, the first thing I should emphasize is that list is not a type, but it's something, but list alpha is a type. So quiz question, just to wake up. If list alpha is a type, what is the type of list? I want someone at least to tell me. Okay, yes? Type to type. Yes, okay, very well. So it's type to type. It's what we can say, like it's like a type constructor or something like that. It takes a type to become a type. So in this sense, it has the same type as set, the way you use it. It doesn't make sense to say it's of type list. No, it's of type list of alpha for a specific type alpha that we care. And the idea is that, for example, I want to capture the idea of having a bunch of elements of the same type, and they come in a certain order, and I can have repetitions and stuff like that. So this is a list of NAT, for example. Does that make sense for everyone? Yes, okay. So saying that I would like this kind of thing does not give me the right to say that I defined lists. In the same sense that saying that I would like these guys here does not give me the right to say that I have defined the natural numbers. So similarly to that, I will give you a very short definition of what the list, how I will define the type list. We know that there are like 3 ways to define types so far, and I will use just the one I find more convenient right now. So I will just list the constructors. And there are like, if I want to establish how I can construct lists, I will separate them in 2 ways. Either I have the empty list, I will give it a name. I could use it like this as a name, or I could write something like empty, or something like nil. These are all common names. So, okay, let's pick nil. I have this constructor, which is already something of type list of alpha. And I have, it's not a very original name when you're looking for a name for a constructor, but usually it's called cons, which is very unfair to all the other constructors. But anyway, that's the tradition. And the constructor, the idea is that we'll take, in this case, if I want to construct this list with this constructor, I would say, okay, get 3 and put it in front of this list, which means that you have already constructed this list. And how will you construct this list? Okay, get 1 and put it in front of that list, and so on and so forth. And eventually you get 7 and put it in front of the empty list for which you have a separate constructor. If you have never seen this thing, it's kind of fun to practice with it and try to prove some things. But the thing I mostly care about here is just to stipulate the induction principle I will have for elements of this type. Because usually in mathematics departments, like you graduate and you only pretty much see induction of the natural numbers, and every time you want to do something inductive-ish on other types, you reduce it to you observe some kind of measure that you can get there. Like if you are doing something on trees, you say, okay, I will use induction on the height of the tree, which is just a natural number. So you pretty much are used to thinking that like induction is only something of the natural numbers, while you could be inducing directly on the structure of the thing you are trying to prove, that all its elements have these properties. So like you could have induction on the lists or on trees or on formulas. Like in logic, some of you, I know that a lot of you have taken logic. A lot of times you want to prove that all formulas have a property, and you say, I will use induction on the number of binary connectives. This is a natural number. No, just do induction directly on the formulas. Yes, Marolis?
I think we do generally see induction on the construction of the formula in undergraduate logic here.
Well, yes, but it's like, maybe you do, maybe you don't. I mean, it's kind of random. It's not like you say, let's see, I mean, that's my impression. Let's see what structural induction means in general. In set theory, you have like something like you see well-founded induction, and maybe study like well-founded relations, and there is a connection there, right? Yes, okay. But in general, like you graduate and you only see natural induction of the natural numbers. A lot of times we'll do it in the number of, in the size of the formula. Like it's okay. Anyway, so it's good. It's good news if it does happen as much as I think it does. So the induction principle, that's the whole point, will not change. It will be the same. All constructors preserve phi means that every element has its property. So, what does that mean? All constructors preserve phi. We have two constructors here. So, if I have a property phi, okay, first of all, what is the type of phi? Help me here, because when I want to prove something like that, okay, I should copy it. Okay. Bear with me for like 3 seconds, or a bit more. Okay, so let's see. What do I need to change here so that this thing will become induction for natural numbers? Okay, I'll do the easy thing. The name of this thing will be nope. Okay. So this will be like the induction for list. Is that okay? It should not be okay. It's the induction of the list of alpha. Okay, because here I put like the type of the thing I'm inducting. I don't know if inducing. I don't know how to say that. But okay, definitely this nut has to go away. This nut has to go away. Okay, suggestions. What do I need to change? I did a few of the changes. And okay, just a second. Where was I here? Something I have not written here is what is the type of phi. So here the type of phi was not 2, yes? Very nice, prop. Okay, so I already start to think what I should be able to prove with induction on lists. I should be able to prove that all lists have a certain property, and this property is obviously something applied to lists of type alpha. So this would be like list of alpha to prop. And maybe you can think that this is like a kind of schema. For each type alpha, this page that I'm writing here is valid. Okay. So what else do I need to change? Suggestions? Yes, come on. Okay. So this thing should become nil. So let's start with the blue things. Like nil preserves phi and the other constructor also, and cons reverse. The good news, this is the whole point, is that the purple thing doesn't really change. It's all constructors preserve phi. Okay, so nil preserves phi, cons preserves phi, and what this thing mean? This is nil here, okay? And yes, go on. So this would be like list of alpha, Good, okay, so actually it's here. I should be looking at this, right, when I'm trying to figure out what's going on. This is Panos? Okay. Okay, good, okay. So Panos observes already that cons is not like successor that it only has one argument, has two arguments, right? So probably I will need to have two for alls here. I will keep asking these kind of things to make connections because they help you catch mistakes. So probably I'm expecting to see two for alls here. On the other hand, there is a very big difference between this argument, this argument and this argument for cons. So this is like the argument that the successor got in the sense that the argument had the same type that it's being constructed. So this is why this type is actually properly inductive or recursive, how you want to call it, while this thing may not be a list, can be anything. Okay, so these things have like a different nature, and this will show up here. So let's try to put this in the correct way. So we would have here, like, for each preserves phi. Okay, so for each, let's call that x or a of type alpha, and for each okay, I like the fact that Panos used suggestive names. I was about to complain about this if nobody did it. So this would be like list of alpha. And what do I write here? The form I had there was an implication. So I'm thinking it should be an implication. And I would like to see how this fits there in the same form as well. Manuel, what's your suggestion?
Phi of A implies phi of cons AA.
What, sorry? Of L, okay. Implies...
Phi of cons AA.
Oh, no. Yeah, they will start a big thing now, I think, right? Okay, let's see. Does this happen a lot? Yes? Okay. Okay, do they do that twice or once? Once, perfect. Okay, so let's go on. Any quarrels here? Yeah, you have a quarrel with yourself? Yeah. Maybe. Yes, I do. Thank you. So, why do I have one thing here? It's because there's only one recursive argument. Why do I have two quantifiers? It's because there are two arguments here, regardless of whether they are recursive or not. And what about this thing here? How many for alls do I have here? Like 0, right? And if I wanted to see this, okay, actually this will become clearer in a bit, what I'm trying to say here. What else do I need to change? So this is not an N, this is like an L, and this is like list of alpha, and this is phi of L. Something else here? Yes?
Nothing like phi empty, phi brackets. Phi empty, phi brackets. 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 Phi
No, okay, so these are synonyms. Sorry for that. Forget about that. We only have this. We only have two constructors here, nil and cons. Thanks for this observation. The other thing, I like synonyms for nil. I might write empty brackets like that or the word empty. I don't know. Okay, so the question is like kind of logic question, but I need it in a more concrete sense. If I can move this around, can I do that? I'm trying to separate the. Okay, now I do need. Oh, sorry. Now I do need an extra bracket, right? Manolis will help me here. Yes. Okay. Yeah. Okay. So I have this, right? Can I do that? Okay. Like that? Yes, you're right. Okay. So this matches this. And this matches this. Okay, yeah. So is this valid? Do I have any problem with like bound variables or something like that? No? Okay, so like for any list, and to make it closer to the way I think of it, like for any list that has the property phi, all things that you will construct, I will not write this down, will have the property phi. So this is how I separate this, where is it? No, sorry. Okay. This how I separate this kind of argument with this kind of argument. And you can prove stuff by induction. You can define things recursively on lists, and I will like put some exercises for us to I don't know to get some experience with this. But for the time being, I have like 3 induction rules. One seems a bit weird, which is like the Booleans, because it's not really inductive. In a sense it is, but it's not really interesting because I don't have any constructors that require arguments like that. Okay, questions? So, yeah.
Το ότι στο list A δεν έχουμε από πριν το list A δεν μας πειράζει επειδή
It's not list A, it's list alpha.
Ναι, list alpha.
We have an alpha lying around. This is the whole idea. So the whole thing I'm doing in this page, it's like for any type alpha. Okay, is that your, okay, so is that okay now? No. Because, I mean, you should have the same problem the moment I wrote this alpha here, right? So, for any type alpha, we have an induction for this type, the type called list of alpha, okay? Okay, so far we have lists, we have the natural numbers, induction, and maybe recursion there. We have to figure out what these things mean. And, okay, I think I'm okay with what I need for now. Any questions about the induction part? No, okay. So, something that we have been doing, and I have like doing this in parallel, and I hope we have been observing it, but it hasn't been concrete yet, is that we have a certain connection between the logic we are doing and types of things. And as an example, I would like to start seeing the logic part, and I will try to develop like a bit of 3 things for logic, which is the following. I will have 2 judgments here, A true and A prop, and I will explain with words what this means. A true means I have a proof of A, so forget truth tables, and A prop means A is a meaningful proposition. So these are the only 2 judgments that I will have, and I'm going to start developing, and I will use this notation, which we have met already, which is called an entailment. And when I write something like a bunch of things entails and then something, like, for example, A true, it means that from these judgments, I can infer that A true. I can build a proof of A. Okay, so let's see like about the conjunction. We have done similar things like for pairs, and now the idea is that what a coincidence, these things like happen, similar things happen in the side of logic that happen in the computational side. So if A is a proposition, from A being a proposition and from B being a proposition, I can infer that this thing is a proposition. Senseful? Hope so. And so this is the formation rule, right? And now actually I want to say how I can deduce things from that. So the idea is that if I have that A is true, and if I have that B is true, I can put them together, and I have that A and B is true. And if you think we have seen this before, I think we have not. This is the whole point. And I have the ways of, so this is the introduction, and I will have the elimination rule. Like, if I have a proof of A and B, I can use it in two ways. I can either extract the proof of A, or I can extract the proof of B. And we prove things, I mean, all these things. I'm doing what is known as Gensen's natural deduction here. I'm specifying rules. I only have one connective, the conjunction, and I have two elimination rules, left and right. And like bunching together these rules, I can have trees that correspond to proofs. As a kind of silly example, I will try to prove that this thing, A or B, true, entails, I don't know, like, I said and, but I used disjunction, entails B and A true. And how could I do that? It's like, okay, I have this hypothesis here, so I will not keep writing true and true for obvious reasons. All the judgments I will be using now are of the form true. So from this, I will get A. I'm using the left elimination rule. And also from this is where commutativity happened. I went on the other side, okay? So also from this, I will get B from the right elimination rule. And now from this, I will put them together, and I will get B, A. This is a very simple proof, a very simple proof tree. So it's a good opportunity to discuss what's going on. Are there any questions of what's going on here? I can read it top down, which means I start here and say, from this thing I can prove this, and then together with this, which I have proven from this thing, and then I'm going down, and finally I have a proof of this, which depends on all the open leaves here. So I don't have the right to say I proved this out of nowhere. I proved this, and I needed what? This and this. They happen to be the same proposition, so I get a way to say I have a proof of that. I may have various copies of this. Okay, and I can read it like bottom up. Okay, the objective is to prove this. I'm reducing this to these new objectives, and I keep going, reducing each one, like one objective more, until I'm done. I'm done either means I've closed this branch, or it's open, but it's on my hypothesis, so I'm okay. So this is a proof of the commutativity of conjunction. It's not like an axiom, conjunction has this property. We have derived this, okay? Yes. So, okay, good. We'll have some, yeah.
Αυτό το notation, πώς λέγεται?
Okay, natural deduction. I will write it down afterwards as well. So this is natural deduction. And this is Gensen's. Gensen is like one of the very main principal names that have built the things we're influenced a lot and built on the things we're investigating, mostly on the proof theory side of things. But there's further things.
Στα givens έχουμε τα θεωρούμε ότι είναι διαταγμένα.
Okay, here I only have one given, right? I mean, you mean here?
Πάνω από γιατί αν όχι, τότε από το induction, νομίζω, το I rule.
Introduction.
Ότι αν τα givens δεν έχουν κάποια σειρά, το να πάρουμε τελικά B true και A true, καταλήγει στο Β και
I'm not sure what you mean, because you say givens, but in this proof we only have one given. I'm trying to prove this, to establish this. And my context, which is like the givens, in which context am I trying to prove this? I only have this thing. Alright? Okay, so if I had like more context, I will answer your question because soon we will have more than one. The order doesn't matter. It will become important when you will not be able to swap the moment we will see what is called like dependent types. Because maybe something is not even pronounceable without having the previous things. This might happen today. Depends on how we'll proceed. Okay, so yes. This is a judgment, yes. The judgment, which means I have a proof of this thing. And I can construct from all those things that I have, which is only one thing, a proof of this thing.
Απλά η ερώτηση μου είναι ότι άμα πάμε και κάνουμε κάτι με το αλφα πρόπ, ας πούμε, τι διαφορά έχει με τα Greek propositions που έχουμε κάνει σαν...
This only means that A is a proposition. You mean, okay, what's the difference between this and this?
Yeah.
Okay, good question. Kind of too good of a question right now. I think we will appreciate this like with time a bit. Don't consider that this is A is of type prop, okay? This is a different judgment. It's not like I have an A in the type of prop, and the type of A is prop. Consider we are not doing type theory right now, we are doing proof theory, and we'll see what kind of judgments there are in proof theory. And the idea is that we'll establish a very good connection between these two. Okay. Any other questions? No. Okay. So I can build like huge trees like that. And okay, I want someone to notice like a similarity of what we're doing here with something we have done. Maybe nobody will notice this. Yes, Areti? This is actual proof? Okay. No, you're still in the logic side. I would like to go in the like computational / type side. Είμαι το? No, wait. One of the Greek letters. What's your...
Δεν είχαμε δύο propositions με το conjunction και αποδεικνύουμε ότι είναι μεταθετικό ή όχι. Το είχαμε αποδείξει σαν...
We have proven, okay, you have actually written a proof like that. Okay, Areti has written a proof like that. Someone has written a proof like that. So we have done that, literally the same thing. But there was also something that we're doing that looks a lot like that. Maybe if you take off your glasses or if you squint a bit, but... So, I will try to find, no, I will not try to find it. Yes, I will try to find it, why not? No. Okay, just give me a second. It's, I think in the last class. I'll find it. Aha, it's here. Okay, here we have something that its nature seems very different initially because it's not like logic, it's not like propositions. It's I'm building a like type for a programming language or something like that, and I'm building the type of product. And first of all, I'm saying what I need to do to build this type. And I say that, oh, look, if A is a type and B is a type, this thing is a type. Essentially, I'm saying this guy here is a binary constructor on types. And this is exactly the same thing that happened. Okay, I will write with this thing here. It was like A is, if I know that A is a prop, I will mess this up. And I know that B is a prop, then this thing is a prop. Okay? One is logic. The thing I just wrote here is like proof theory and logic. The other thing comes like from programming language computation. I have a type. But the similarity doesn't stop there. The important similarities extend to like introduction elimination, which have exactly the same form. Here I had, what did I have there? I had like A true and B true, and I would conclude that this is true. And here I'm already starting to appreciate that I have some like further information here. I have like a reason for why A could be true, a reason for why B could be true, and maybe I would like to influence myself from the computational guys and say, how about I start naming my proofs as well? So I don't only want to say A is true, I want to say, look, small a is a proof of big A. And the same thing goes for elimination. I have like 2 elimination rules here, it's exactly the same thing. So let me go back to logic now. So like we have our first realization, like maybe I have to do this, write something like logic side, and then I have something like types. And we're establishing that there is an intimate connection between conjunction and the product of types. And so this thing would correspond to the out left, and this would correspond to the out right. And I already can have something like a fruitful idea from back and forth that say, okay, maybe it makes sense to consider what happens if I start giving names to these things. Like I have a proof of A, I have a proof of B, and how can I construct a proof of this guy? And now I have access to the objects. If the idea was maybe in the first class or the second class that we want the actual proof things to be on the same table as the other things, mathematical things that we're proving, so that I have access to them and I can operate with them and build new things out of them and all of those things. So, okay, let's go back to the table. No, there was a question by Sotiris or not? Yes? Yes.
Couldn't it be a coincidence that...
if it's a coincidence, that's
yes,
what...
that you're building a type and building a proof end up looking similar and behaving in a similar way.
So the whole idea is that this, you can call it a coincidence. The whole idea is that I'm trying to convey throughout this, the whole class until the end of the semester, is that it's the same thing, the same idea, that we capture it from various different angles. That was like the triangle, the Holy Trinity I was talking about, and we'll keep doing round and round. And the idea is that anytime you need some idea here, you can see if you already have a corresponding concept there or there that you have not translated yet, and there you go, you have a new idea in the other aspect. It's essentially the same thing. It's different. I would say like it's 2 sides of the same coin, but it's like 3 sides of the same coin. So the metaphor doesn't work so well. So at this moment, you might say something like, okay, so I have conjunction, I have in the types I have like cross. In logic, I have implication as well, right? And then you wonder, do I have a corresponding concept in the types? So yeah, ideas, yes. The function type, right? So essentially, this means that we will visualize. We have done that already. Implication as something that transforms proofs of this thing to proofs of the other thing. And okay, what else could I write here? The bottom. I have a bottom in the logic, right? I mean the falsum, right? You might prefer negation, but we think that we have defined negation in terms of the bottom. So the idea is, okay, what do I have in types as a bottom type? Ideas, yes.
Non-type.
And a what?
And non-type.
What's a non-type? How? We haven't seen it, but so this is good news, because we might figure out a concept that we have not figured out yet. Okay.
Type that has no elements.
Okay, like an empty type.
Yes.
Okay, and some of you have programmed like maybe in C or Java or things like that, and they are used maybe to saying functions like this, and we say like that. Okay, for those who haven't seen it, the usual visualization of these things is that, or even void, okay. Has anybody here never seen this? So that I should not explain this. Thank you, okay. So this is like how the C programmers think this. F actually takes no arguments. This is what the void corresponds to. And it already produces an integer. And an example of this thing would be like a function that you will call it like that, and it will return something like 5. On the other hand, the other thing is like a function that takes an integer and doesn't really return something. And an example of this would be something like maybe, I don't know, it prints something on your screen or something like that. So it takes it does something like that. It prints 42 on your screen. It doesn't really return anything. It just has a side effect. It sends something on your screen. And this is something like, it takes no arguments, and it also returns nothing. Okay, so, like if this corresponds to the integers, let's say, it's not reality, right? Because tons of differences. First of all, int is like a finite set of elements for the C programming language, and arithmetic does not really work the way we are used to it working, but the question is like, to what the void corresponds? And I will admit it's a trick question. Yes?
It's a special place in memory, like the empty null pointer.
Oh, okay. This would be very implementation specific. Okay, forget. You know too much maybe of implementing this stuff. Like, I'm asking what is the mathematical concept corresponding to this. Like in the same sense that int is also some kind of implementation of bits. Depends on your
Empty set.
The empty set. Who agrees? Who disagrees? You agree and disagree as well? Okay, who agrees? Okay, who agrees? Let's see. Okay, who disagrees? One, okay. So democracy doesn't always work. Say something.
I would propose something like a zero tuple.
Zero tuple. Only one problem with this. Zero tuple is like an element. What would be the set or the type of this thing? When you say zero tuple,
Maybe it would be a type of itself.
a type of? This would be a type of itself. I mean, what would the type of this thing be? You have programmed in Haskell, and as confusingly, Haskell uses exactly the same notation for the. Haskell would say something like that. Okay, but these two things are different. Okay, and it's like a convention. Okay, Lazarus is absolutely right. But first of all, let's see why it makes no sense, and it's a terrible name, void, right? Because void makes you think of the empty set. Let's say you have something from the empty set to the integers. How can you use it? In order to use a function, remember the elimination rule of the function. How do we use functions? We have to have also something of the type of its input. So I would have to have something of this type, and then I would be able to say, okay, then f of a is of type integers. So if it was of this type, it would be something that you could never use. You could never call it so that it would produce something. And similarly, there is an even worse problem. So this is not terrifying because it just tells you, you have a function that you will never call. So forget all this business that you have here, that you are writing this thing, because it looks like you are calling a function, and this function is uncallable, unusable. The worst thing is that, like, if you have a function like that, it means that you could use it. So let's write the type of this function. You could use it together with any integer of your choice and apply it to this integer, and you would produce something of which type? Of the empty set. Okay, so this is a good reason that the answer empty set is not valid, right? And just to defend all these things I was saying like a few classes ago about the notation here being confusing when you are used to seeing parentheses as the thing that calls the function. If we write it like that, we're starting to appreciate that this thing actually makes more, what Lazarus said makes more and more sense. I have f, and I'm applying it to something. This is function application, and this is just its input. So I need a type. What's the whole deal with functions from type void? The idea is that the function will not receive any information that might affect its return value. It's like, I want to be able to call you, but I don't want you to get any information as input from me. So it means I need a type that only has one element. Because from the moment you have two elements, there is already extra information. The function might ask, which of the elements did I get? But if you have an element with only one type, you cannot even ask this thing. The idea is that, think of it as a little coin, right? This is a little coin that lets you call this function. So it's callable, and it will produce something. So we have two ideas that we want to go around here. First of all is like discover the type, I will call this type like that. Thinking like this. And I also come to the conclusion that I probably need a type with only one element that I will write like that. So let's quickly define these types. I will call it unit, because I really don't like the confusion of using tuple and tuple. And I need a name for the only thing of my type unit, and I will call it star. Okay, I think it's a better name. But you can use any name you like. It doesn't really matter. The only thing that's important is that it's only one. So this is of type unit. So Haskell programmers would write this like this. Okay. And the other type I need to do to define is the empty type. And I will also call this like one, like this, and this I will call it like this. And I just defined it because it has zero constructors, but it better have zero constructors, but because I don't want anything to be constructible there. So let me go on with this little table here.
Sorry, what is unit type? I didn't understand.
What, sorry?
What is unit type?
The unit type is the type I'm defining right now. It only has one constructor called star. Okay, and this constructor doesn't take any arguments. It's already an element of this type. Remember what we did with bool? We had like two constructors, one called TT and the other FF. This is another type, has only one constructor, and the constructor is called star. So it's like a singleton, right? If you think of this like in set theoretic terms, and this is like the empty set. It's like a singleton that I single out in a sense. Okay, so let's fill in some things here. What goes here? So if I think of what's going on with this type, it's a type that has only one element, and this means that it has useless information. I shouldn't be able to extract useful things out of this. If you tell me, aha, I have an element of the unit, there's no further information. I already know we have an element of the unit. I cannot do anything with that. If you say, aha, I have a bool, I can say which bool is it and do something, okay? So the question is, what concept should correspond here? Yes, Manolis? The negation of bottom, okay. It will end up being like equivalent to that, but we could also say, okay, let's try it as a primitive thing. Okay, and like I have a truthness, the same way I have falseness, I have truthness, because I'm also trying to appreciate the idea of gaining new concepts. Like, you jump to computational things, you may gain new concepts. To algebraic things, new concepts. To programming things, new concept. And now, especially on the algebraic sides, maybe you want to dualize a concept. So, to get new concepts as well. So what the suggestion of Manolis here, we can see this as a way to, let's dualize this idea and gain a new one. We don't know what dualize means yet, and we will fully appreciate this doing order theory and category theory. And I'm planning to start this on like the next lecture. So like probably the next lecture will start a crash course on category theory and order theory, because I'm reaching the point that I'm missing vocabulary. It's becoming like a bit too challenging to say useful things. But we have some more useful things that we can say a bit here and there. Anything missing here? Okay, and maybe we'll have some idea of what could be missing. And another way to see what's missing, which also is useful, we have this idea. I mean, we have already met something like this. Okay, and we have met something like even more interesting, this. This is just clarification. And we have seen that actually, if I just change notation here, this looks like this. I hope I'm not doing something very weird. So there is some kind of arithmetic on types. Like I have multiplication, I have exponentiation. Apparently I have 0, 1. And I don't deserve to call things arithmetic just because I'm using some symbols. I should have laws like this. I mean, these things are what justifies the word arithmetic. And now someone might say, okay, then probably this thing, 0 times alpha, should be, oh, definitely not alpha, 0. So you will prove this. I mean, it's an easy exercise. Find a function that translates 0 back and forth. And probably I should have things like this. And now I'm in a situation that I have arithmetic where I have multiplication, which was so easy to grasp, exponentiation, 0, 1. There's definitely something missing, right? Yeah, I mean, where is addition? And it's very weird. I really want to understand this. I haven't understood this yet. Why it's so difficult when you're doing programming and types and mathematics or set theory or whatever to understand addition. I mean, imagine if you go in an elementary school and say we'll start with multiplication, and then the challenging thing will be to teach addition. So there is definitely something that might be missing here.
Like disjunction, no?
Yeah, and so we have another way to think that something might be missing. Say, hey, in logic we have like disjunction, so let's find what kind of thing there, and it will end up to be the same thing on the two sides that is missing. So it's time for a break. Okay, so we have established just an idea, not the whole thing, that probably we'll have an arithmetic on types, and I've given like some examples here, and maybe I should like write some more because maybe you think it's just like these trivial things. But the idea is that we'll have like, I don't know, pick your favorite arithmetic property, like this, maybe. So what do you think that this should be equivalent to? Somebody? What is this? This is, how is this called? No? Yes? Maybe, I don't know. I don't know the Greek name for this. It's distributive, yes. Is it this one? Is he right? Is he correct? Yes? Okay. Associativity is proseteristiki, right? Okay. Yes, okay. So regardless of the name we give it, it should be this thing, right? Probably. Okay, so that's wrong. Yeah, I don't know how to apply, okay, the distributivity property. So it's like this. And in order to be able to write this, I have also a syntactic worry here. These things will end up being implicit because I will say that this has like higher precedence than this, okay? Just like for obvious reasons. So we have like distributivity and we have like, I don't know, like pick your favorite property and try it. It's not guaranteed, obviously. You see like five properties that hold, that doesn't give you the right to say that everything will hold. But yeah, I mean, it makes sense that it will. So we have this arithmetic and, okay, by the way, this is like binary distributive, right? Because, I mean, you have two things and you're distributing multiplication over two things. What would be the unary multiplicative? It's kind of trivial. But what would be the zero-ary distributivity? Okay, zero-ary distributivity, it seems like we're missing something. In order to say zero-ary means something that looks like this for the case that I'm adding zero things, right? Because here I'm adding two things, and I have two things here. So what happens if I'm trying to add zero things here? What's the zero-ary version of distributivity?
What would the unary mean?
Unary is kind of lame. I mean, it's this. Unary is that this should be equivalent to this, which is kind of trivial and obvious, but this is the unary version of distributivity. You are distributing something over one thing. It's just this thing. So what happens if you distribute something over zero things? Exactly, it's this one. Usually you don't see it as distributive property, but this is the zero version of distributivity property. Does that make sense? I mean, this means pretty much that if you add zero things, you should get zero. And this leads us to another question. What happens if you multiply 0 things. What's the correct answer here? Suggestion? 1. Yes, why not 0? I mean, why 1? Or depends which of the things you want.
Because it's kind of the identity element.
Yeah, exactly. So observing that you have an identity for a binary operation, if you want to generalize this to more than 2 things, you don't care about the identity element. I mean, as soon as you have a binary operation, call it how you like, you can if it's associative, you can generalize it to applying it like big heart, apply it to a bunch of things like A, B, A, C, C. I mean, operate on them. Okay, you cannot do that if you want to have no elements at all, unless you have an identity element. So you have an idea of saying what is the empty sum. It's 0 because 0 is the identity element of the addition. And what is the empty product? It's 1 because 1 is like the identity element of multiplication. Okay, so we have, to sum up, we have some arithmetic on types, which is interesting and can give us new ideas. We have this junction, and we don't have yet, we haven't figured out how this will be used. Let's see this junction, because I haven't written it on the logic side. So first of all, to get used to it, if I have A prop, and if I have B prop, I should be able to form the disjunction of these two, and it will be a prop. So I'm not doing deep stuff here. Essentially, I'm saying I have a binary construction of propositions. And how do I introduce it? I have 2 ways to introduce it. Either knowing A, I can say that this is enough for me to say that I know A or B. Either knowing B, I can deduce the same thing. So here is one aspect of dualization. I have 2 introduction rules for this junction, while for conjunction I had like 1 elimination and 1 introduction and 2 eliminations. Now I have 2 introductions, and probably I suspect I will have only 1 elimination. And this elimination is like the first rule that's kind of tricky to write. I need to say how I can use this junction. We know that from the language we are developing, how do we use this junction? It allows us to split the thing we want to prove in 2 things, and we have to prove both things. So I can start putting it in a form, like if I have some goal G here, and I want to prove that this is true, and I know this, how can I use this? Well, I need to reduce the proof of G into 2 proofs, 1 from A and 1 from B. So it should be something like that. Okay, so let's see what this means. If you have a disjunction, and from the left part you can deduce G, and from the right part you can also deduce the same G, then you can deduce G. Okay, this is how you use disjunction. Are we okay with this? The idea of disjunction? Yes?
Είπαμε ότι πρέπει να ισχύουν και τα 2 ταυτόχρονα.
Are you talking about these things?
Ναι.
So, you want to prove G, you reduce it to 3 things, okay? You need to close all of them. I mean, you need to establish these things. This is why when you separate in cases, you have as a given A or B, and you want to guarantee G. You can look on this given and say, okay, it could be an A, it could be an B. You don't have the right to say it will be an A. That's the whole point of the junction. So this is why you need to close both, to guarantee both these things.
Why? Sorry, because if you only have the first 2, it's enough, no?
Okay, so let's see what happens if we delete this thing, right? This means that I will not even be able to prove something like from A or B, I will not be able to deduce B, right? Because there is a chance.
Yes.
I think the metaphor with the box that you don't know what's inside works well here. You want to give instruction to someone who will open a box, So you have to give instructions on what happens in either case. If you find inside the left thing, this is what you have to do. But what happens if you find on the a right thing? You need to tell them what to do as well. Otherwise, it's half the instructions. Does that make sense in mathematically speaking, logically speaking?
Yes, it's just
Okay.
that we want to prove G, right? So why do we care about the truth value B?
Okay, first of all, it's not a truth value. I know that the word is confusing because I'm using the word true. Forget truth value. A true means I have a proof of A, okay? It's just to make this clear. So, you have A or B, right? From A, you can deduce G, right? And,
Okay, I understand.
okay, good. Okay, yes?
I need one clarification.
Okay.
So you can have a box and a cat.
You have a?
Box, cat, the Schrodinger cat.
Okay,
It's dead or alive.
okay.
So if the goal is to determine what happened to the cat, A is alive, B is dead. So if A is alive, then I determined what happened.
Wait, because what you're saying, you have the disjunction in the goal.
Yes.
So you are here.
Yes.
Okay, sorry. Okay, go on.
I'm saying that if the goal is to determine what happened to the cat,
Yes?
and I open the box, and the cat is alive, then I determine what happened. The cat is alive, and if the cat is dead, then I also determine what happened. That's why we need B, because we.
Okay,
In both cases, we can't determine if that is the goal.
I'm a bit confused by your analysis here because I think you are mixing these two things. Like,
Probably.
if you are trying to prove the disjunction,
Okay.
there's no box to open.
Okay.
There's a box that you need to fill in.
Okay.
And you need to decide if it will be filled in with the left thingy or with the right thingy.
Okay.
Okay? So, how does this correspond to a type? I need some notation. So, like, let's do type and computational things again. So, the idea is that if A is a type, and Vita is a type, and this is also the answer of why don't we get union to do stuff? Because it looks like some set theorists might be able to do more things because they get to unite stuff, but the idea is that they start losing information there, and we want to be able to not lose this information. So here I will say that this is also a type. This is just the formation rule for plus, and now I need to say what the introduction and elimination rules are. So let's copy this idea. I just need notation. So if I have a proof of A, I'm using terminology of logic while writing like type theory, and this is on purpose. If I have like a proof of alpha or an element of type alpha, this should be enough for me to construct a box like the thing that Konstantin was saying, a box of type alpha or beta. Where will I place it in the box? In the left part, right? So I should be able to construct something of this type. And similarly, if I have something of type beta, I should be able to construct something of this type. I just need to figure out a way to say that. And I will use a bunch of notations as well, dualizing the notations I have for products. I could say something like in left A or in right B. Or I could say something like the lefting of A or the righting of B. Rightment, I don't know. Invent your own English word for that. I think I'm fine with these notations. I don't need anything more. Yes, Arathi. The two rules? Okay, there is an objection here like what the hell is this vita? And the idea is that for any vita you like, if I have an alpha, an A of type alpha, pick your favorite vita, I can create something of this box. Oh, sorry. I can create something of this box. I will put it on the left hand. I don't care what the type vita is. I already have possessed something of type alpha. So if you give me a box of type vita, I don't even need to know which type this vita is. I can place it on the left part, and now I have something of type alpha plus vita. So this type unites all elements of type alpha and all elements of type vita, but it doesn't lose the information of if it's a left thing or if it's a right thing. If you're thinking of two sets that are distinct, no, not distinct, sorry, disjoint, thank you. This information is never lost because there is not, you see something, you say okay, it's from A or from B. They are disjoint, so you see something that belongs to A, you know it came from the left-hand side, let's say like that. But if they have an intersection, this information is lost. Even worse, if it's the same set, it doesn't really make sense in set theory to unite A with A. Here it does, okay, because you have the left A's and the right A's. And you interpret them in a completely different aspect, okay? So just to give a motivation for programming, maybe you have this is not good programming, but I will say it anyway. Maybe you're using this type, so you have the left integers and the right integers, and maybe you have the idea that the left integer corresponds to how many items this client bought, and the right integer is some kind of error. And the integer says if it's 404 error, or I don't have this client, or the database connection, permission, whatever error. You have integers corresponding to errors. This is bad programming, but anyway. And so it doesn't really make sense to say, it's 3. I want to know, is it a left 3? So it means they bought 3 items, or is it a right 3, which means it's error code 3? So it really makes sense to keep this information where you're coming from, even from a programming point of view. Okay, so I will scan this way. Yes, Sotiris.
Okay, so on Artie's question, it would mean exactly the same thing if on the bottom left we replaced beta with C, and on the bottom right we replaced A with H.
I just don't like the fact that you changed the alphabet. I mean, let's
change it on purpose to show that we don't care what it is.
No, but you changed it from the Greek alphabet to Latin alphabet on purpose.
This was no.
Okay, so this is the thing I didn't like. So yeah, this thing is the idea is you can place whatever you want here. Vita here is free,
yes.
Right? And similarly on the other hand side, yes. So, and this is stated here in the sense that I don't need to know anything else here.
On the right side, you deleted the wrong one.
Thank you. Yes, I did. So I deleted both Vitas. I should delete Vita on one hand side. Okay. Okay, thanks for this question. Does that make sense? Okay, so when I have two types, alpha and Vita, I can consider the type of not putting them all together and messing like that, labeling them all, the left A's and the right A's, and now my type consists of left A's and right B's, and of no A and of no B. This is a common mistake. The first time you see that, you think that, so 32 can be seen as a type of this thing. No, it cannot. Neither of this thing. Similarly, Thanos is not a type of int plus person. The writing of Thanos, the right-ment of Thanos is an inhabitant of this type, and the left-ment of 32 is an inhabitant of this type, but just 32 is a type error to consider that, okay? It has not been tagged, it hasn't been labeled as a lefty or as a righty. Yes, Manolis?
I have two questions.
Yes.
First of all, so when we say in A is a type A plus, plus beta, is there an implicit beta as a subscript to inner or something? Is it a different thing for each type beta?
Yes, perfect. So implicitly, I have here, very good question, this is the in left Vita, and this is the in right Vita, in right alpha, which we will never use because it's never write explicitly because it's always inferred by the type. Okay. Yes. Other. Yeah.
So this is basically disjoint union.
Yeah. If you're trained, if set theory is already in your blood, you say this is disjoint union. So with the exception that in set theory, union is set theory likes unions in some sense, and then
It is outer union.
What?
Outer union.
I'm not sure about the terminology, but
It's usually you call it something like that. It's called disjoint union, or
zeros, you label one thing with zeros and the other with ones or something. believe.
Yeah, so usually you find some way to take two sets that might intersect, and first of all, it's like you paint these guys a different color than these guys, 0 color or 1 or left or right, whatever, and then you use the actual union, because you consider union like a more primitive or more essential operation for set theory, while here it's like plus is the essential thing. Union doesn't really make sense here.
Yeah, and conceptually, like as what we want to do with it, intuitively, maybe it's like a disjoint union.
So when we need to wait a bit to gain vocabulary, categorical vocabulary, categorical, I don't know, to actually say, in the world of sets, plus means disjoint union. So it is this thing translated to the world of sets. Yes, Κωνσταντίνος.
Από ό,τι καταλαβαίνω στην ουσία δεν έχει να κάνει με πρόσθεση, είναι public περίπου.
Wait. Are you talking about this?
Ναι, που λέμε ότι στους τύπους είναι το αντίστοιχο του disjunction και το έχουμε να το σκεφτόμαστε ως πρόσθεση. Δεν είναι όμως πρόσθεση, γιατί
you're asking if it deserves the name sum, okay. Again, usually all these debates of does this thing deserve to be called that thing, category theory gives the answers. We have established the names for these things, so it's settled. We cannot defend this yet. We only have some intuition, but I think that our intuition agrees that it should be called addition because it has pretty much all the properties you know from arithmetic with addition. If you see this kind of properties, why wouldn't it? And one more argument, which will not be the final argument will come from category theory, is if you look at the cardinalities, and if they happen to be finite cardinalities, and the type alpha has 5 elements and the type beta has 3 elements, alpha plus beta will have which is not what happens in set theory. In set theory, you have the best you can say is something like A union B, the cardinality of this is less than or equal to A union B, plus B. So you already suspect that the notion of union is not the correct notion for sum, for the addition. While in types, you will have the cardinality of this thing is equal to the cardinality of this plus the cardinality of that. Any other questions? Yes?
Again, as for the above thing that if it was disjoint union, it would hold again.
If it was what, sorry?
If it was disjoint union, the cardinality of the disjoint.
Yes, exactly. Yeah. So this is one more reason to think that probably disjoint union deserves the name of addition here. And when you do set theory, and you want to define the addition of cardinal numbers, you end up using it to define that. Okay. What's missing? I want to get you in the mindset of discovering something in one part of the triangle, see what's missing on the other one, to discover a corresponding new idea there. So can somebody spot something that's missing in the logic side? Let's see this, which was very simple, right? What's the name? The conjunction. What's missing here? When I compare it with what? With the programming computational aspect, which is the type, which was the Cartesian product. Someone? No. So, this is the logic equivalent of the product of types. Am I missing something, or do I have for each thing I have something? And yes.
From the logic side, we don't have the for all and yes.
Okay, so this is another thing that's missing, but I was not there yet. Okay, so and this will be rather challenging, not so much, but okay. More challenging than the other ones. For all and exist, and there is one. Okay, since we're on this column here, and we have discussed this column a lot because we started with logic pretty much. What else is missing in logic? Yes. No, because negation will be if I have this, and this I have negation, and you could argue about this thing as well. For a good reason, which we will see. I would like to talk about this independently. We'll see that this fragment of logic here, you can see this as a group of guys, and the other, this again as some kind of other thing. But there's something essential missing in logic part as well. Yes? Yes, the equation. Το ίσον είπες, okay, equation. So this seems a bit challenging, and this will end up being the most challenging. Okay. So let me go back to the thing that I was spotting to be missing here. We have a formation rule here, which corresponds to the formation of the type, right? We have introduction elimination rules for propositions, for these judgments of being true. What do we have on the other side that we don't have here? And maybe we don't even feel that this is missing here, but we should appreciate it and understand that no, it's here, but maybe we don't realize it. Where's the computation? Where are the vitas and ditas? Okay, so this thing should manifest itself in some way when I'm doing proof theory. The whole idea is that it's one thing and we're approaching it on different ways. So let's say I will just write one. I will just design something here, and I hope it will make some sense. Let's say that I have here made a huge effort in my life, and I have managed to derive A, and here, like I have made different efforts. Let's call this like D1, and here I have another proof of B. And now what I want to do is like put them together. Again, this is implicit. I have a proof of A, blah, blah. All the judgments I'm writing in proof trees means true, 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 true. Okay, so I want to put them together. Introduction of conjunction, and create A and B. And what will I do now? I will extract, let's say, the left part to get A. And this is a valid proof of A, supposing that this is a valid proof of A. Supposing that this is a valid proof of A, and this is a valid proof of B, this is a valid proof of A. And in a sense, I would like to say that this tree here is not fully computed. There is something, this proof computes into something simpler. And in a way, step by step, do more and more calculations in the same exact sense that when you're a child and want to do something like through 3 plus 2 times, 1, this is not fully evaluated. There's computation to be done. So this, in a one step, it will become 5 times 1. And then in the next step, this will become like 5. Okay. So this thing here is like this. There's further computation to be done there. And can somebody imagine what the result of one computation step would be to this proof? You take this proof and you transform it into what? It should be a proof, still be a proof of A. Yes? Exactly. So it will be like this thing, right? It will simplify to this. You got this thing, and you had a bunch of proof there. You put them together, and you only extract the left part. You could just do it in. You could just be done with the left part. And this is the thing that usually when you see it in proof theory, you say this is completely silly because nobody would ever write a proof like that. I mean, no human would do that. But the idea is that you don't have control of what happens and what shows up during a computation. Like maybe after a lot of time, you ended up in like this thing, times 2, and you do some calculations here and you end up, this is 0 times 2, and you say, okay, so this is actually equal to 0. It's not like someone started saying, I will write this very weird, complicated way to describe 0. So for the same reason, you understand that n times 0 is equal to 0 is essential, and you will not say something like, nobody would write n times 0, they would just write 0. They will not write this directly. It's something that shows up during computation. And you need this rule in order to compute the final result. The same way you need n times 0 is equals to 0. So we have this idea that proofs compute as well. Okay, I hope I will leave this as an exercise to decide if this is a vita or an eta, and if it's one of the other, what is the corresponding the other side, and what I can say on the proof theoretic side about this. Any questions on this? No, okay, very nice. So we still have a challenge, like where is my table here? So what we do with for all exists and the equality and stuff like that. And a very nice idea comes from like programming in certain programming languages. So maybe it's a good time to start talking about dependent types.